Good morning, everyone. So last time we have seen about the some concept involved in Gibbs phase rule, like a component, number of phases, and degree of freedom. So what is the degree of freedom? A degree of freedom is an independent physical parameter such as temperature, pressure, concentration, and in the formal description of state of physical system, that is the degree of freedom. Means the number of variables such as a temperature, pressure, concentration, but in terms of degree of freedom we have to fix the number of variable. So today we are going to discuss about the derivation for phase rule. So actually there are the three main important conditions are required to study the multi-component system with having the several phases. So we have right here, we know the what is the phase rule. F is equal to C minus P plus 2. So this is the phase rule. Mathematically, phase rule is expressed by F is equal to C minus P plus 2. What is the F? That is the degree of freedom. C is number of component, P is number of phases, and plus 2. But how the phase rule is derived? That is the question. How to derive the phase rule? So to study the some condition for multi-component system, if you consider any multi-component system, and to study some its condition, we require the three most important conditions. Means suppose if any multi-component system, suppose we have multi-component A plus B C. Okay, these are the multi-component and we have system. So we have three components and we have different phases in this system. So if this system in equilibrium or it will not be in equilibrium, it requires the three most important conditions. So if this system satisfy three conditions, so you can say that this system is in equilibrium. So to derive the phase rule, if you consider the system, it must have the three most important condition and it must have to satisfy these conditions. The first condition is thermal equilibrium. Thermal equilibrium. That is the first condition which is must for derivation of for phase rule. For any multi-component system with having several phases is called to be in equilibrium when it satisfies the first condition, that is the thermal equilibrium. So we know that in such system we have three components and we have the number of phases like phase 1, phase 2 and phase 3. So all these phases must possess the same temperature. What is the one first condition? Thermal equilibrium. As per the thermal equilibrium, if we consider the system or system with having the multi components and we having the multi phases, each phase must have same temperature. That is the first condition. Okay, now if we have component A, component B, we have phase A, small a, and phase B. So therefore the condition says that the temperature TA will be equal to temperature TB. That is the one of the important condition for equilibrium. Okay, now let's see about the second condition. Second condition is mechanical equilibrium. The equilibrium must have the mechanical equilibrium. So what about the what is the actually mechanical equilibrium? Again, if we have the multi-component system, we have multi-component, we have multi-phases. So in each phase, the pressure should be same for each phase. Okay, Again, you can consider here the example, the multi-component system. If we have component A, component B, component C, so what is the mechanical condition? The each phase having the same pressure. That is a mechanical equilibrium. Now, the third one and most important condition for equilibrium, that is a chemical equilibrium. The third condition, that is a chemical equilibrium. For any component in each phase should be equal to each phase, but the chemical potential should be equal for each phase. Again, you can consider here the multi-component system. If we have the multi-component system, so what is the chemical equilibrium condition? The condition says that the chemical potential for each phase should be same. What the chemical equilibrium says? The chemical potential should be same for each phase for given component. So this is our third condition. According to chemical equilibrium, the chemical equilibrium of each phase should be same. So what chemical, that is a mu denoted by chemical potential. What is the actually chemical potential? It is the change in free energy. What is the chemical potential? It is a change in free energy with change in number of moles of any component at constant temperature and pressure. So you can write here mu is equal to change in free energy with change in number of moles at constant temperature and pressure. So this should be equal for each phase. That is a chemical equilibrium. For each phase, the chemical potential should be same. So these are the three important conditions for any equilibrium for multi-component system. If any multi-component system should for satisfy these conditions, so it is possible to derive the phase rule. So let me start from the derivation. These are the some basics for derivation for phase rule. Now let me start from the phase rule. Let me explain you in simple language, then I will go through the concept which is given, which is provided in textbook. Derivation of phase rule. The first condition required to derive the phase rule, that is to determine the composition of each phase. In previous lecture, we have discussed that how to justify, how to decide, how to determine the composition of each phase using the components. So chemically we have expressed through the component, but if we determine the composition of each phase in terms of concentration, then we need the concentration of each component simply. So in previous lecture, we have discussed that composition of each phase can be expressed by using the component. We have taken example for this equilibrium in previous lecture. So For each phase, we have expressed through the components. So this system was the two component system, and each phase we have expressed through this component. But in terms of concentration, if we have to determine the composition of each phase, suppose we have the system which having the multi component, and each phase, if we want to determine the composition of each phase, then to determine the each phase, it is necessary to determine the concentration of component. Okay, so in this terms, in this case, we have determined the composition of each phase through the concentration. So suppose if we have system which having the three components, that is a multi-component system, three component, then simply the concentration of component can be calculated through the C minus 1. Okay, suppose if we want to determine the composition of each phase in three component system, so what are the number of components? That is the three number of components. So if we need to determine the concentration, then simply 3 minus 1, that is a 2. So there will be the two concentration required to determine the each phase of system. If we have the one component system, so C is equal to 1, therefore C minus 1, that is a 0. So for one component system, we do not need concentration to express the composition of each phase. Okay, if we have two component system, if we have two component system, suppose we have system with having B and lead and silver. So this is a two component system, so we have two component. So if we need to determine the concentration, then C minus 1, you can write here 2 minus 1, therefore 1. Therefore we require one concentration, at least one concentration to express to determine the composition of each phase for this system. This system is a this is also the multi-component system with having more than one component. So again, for this system, we require one concentration to express to determine the composition of each phase. Now, if we have three component system, if we have three component system, suppose we have system with having water, toluene, acetic acid. So number of components are 3. Okay, so if we have system water which is equilibrium with toluene, equilibrium with acetic acid, and we know that this is a multi-component system and there are number of phases will be possible for this system. So suppose this is a one phase, second phase, and there is a third phase, and if you want to determine the composition for each phase, that what the condition is necessary to determine the composition for each phase, exactly we need to determine the concentration of component. How can we determine the concentration of component? Simply C minus 1. Okay, so we know that this system is a multi-component system, therefore component is equal to 3, then C minus, that is a 3 minus 1, which is equal to 2. So we need at least two number of variable of concentration to express the each phase, composition of each phase. What we need here, we need at least two variables of concentration. Okay, we need two variables of concentration to determine the composition of each phase. So that is a concept here. Now talk about the concentration of variable. What are the concentration of variable? I am already discussed there, but even the authentic definition is provided in your textbook, that is the product of number of phases and that of concentration of component. What is the concentration of variable? It is the product of number of phases, that of concentration of component, means it is the simply product of phases and concentration for any component which is given in equilibrium. So how can we write? We can write the variables of concentration in this term P into bracket C minus 1. Okay, now we have the again two remaining variables. Okay, what are the remaining two variables? We know that we have in this phase equilibrium, mostly we consider the three variables. Which are the these variables? Concentration, temperature and pressure. Okay, now remind your last 5 minutes that I have told you that for any system the condition, what are our condition? The condition first was thermal equilibrium condition. For any equilibrium condition, temperature will be same for all phases, for all components and all system. Okay, so we have considered temperature here, one variable. Okay, then again we have discussed that mechanical equilibrium. Okay, so in according to mechanical equilibrium, for each phase pressure should be same for each phase. Okay, therefore pressure will be considered as a one variable. Again we can write here one, then we get total number of variable C minus 1 plus 2, that is a total number of variables. Now the most important thing is that you can write here the how can we derive the phase rule? F is equal to total number of variables minus number of relations between them, means total number of variables आणि त्याचे रिलेशन विच इज इक्वल टू डिग्री ऑफ फ्रीडम. आता काय काढायचे आपल्याला? नेमकं सिम्पली आपल्याला टोटल नंबर ऑफ व्हेरिएबल्स काढायचे. तर आपण इथे काढले टोटल नंबर ऑफ व्हेरिएबल्स. सो मोस्टली वी हॅव थ्री व्हेरिएबल्स. ओके, द फर्स्ट वन द कॉन्सन्ट्रेशन, टेम्परेचर अँड प्रेशर. अँड हाऊ कॅन वी डिटरमाइन दिस variables of concentration? You know already that we have discussed here that for each composition, for each phase we need to determine the variables of concentration. And how can we determine the concentrations of variables? Using the number of component and using the C minus 1. So here we need to find out the degree of freedom. Degree of freedom, that is a fixed variable, and you can say that unknown variables. So total number of variables that we have and the number of relations between them. जे रिलेशन आहे व्हेरिएबल्सच्या त्याला आपण म्हणतो नंबर ऑफ रिलेशन बिटवीन द देम. देन हाऊ टू डिटरमाइन द नंबर ऑफ रिलेशन बिटवीन देम? ओके, हाऊ कैन वी डिटरमाइन number of relations between them? We know that total number of variable P C minus 1 plus 2. Now let's talk about the number of relation between them. Before finding the number of relation between them, we need to discuss about again chemical potential. We have already discussed about the chemical potential. What is the chemical potential? It is the change in free energy with change in number of moles of any component at constant temperature and pressure. That is a chemical potential. And what is our condition? The chemical potential should be same for all phases. ठीक है, काय कंडिशन आपली? जे केमिकल पोटेन्शियल आहे सेम पाहिजे प्रत्येक फेज साठी. दॅट इज अवर कंडिशन. नाउ let me talk about the number of relation between them. So if we have three component system, just consider three phases of any component system. ठीक है, just consider three phases for any system. Suppose component A, component B, component C, which having phase P1, P2 and P3. So basically we got two equations for this condition. We are getting two equations for this condition. What I am saying you, if we have three component system A, B plus C, and this is a multi component system with having phase P1, phase P2 and phase P3. So we have three phases. Okay, for three phases the chemical potential should be same for each phase. Okay, what I am saying, the chemical potential, that is a mu1, mu2 and mu3. What is the condition for chemical potential? Chemical potential should be same for each phase. So chemical potential, that is mu1, mu2 and mu3 will be same for each phase. Now you can see here mu1 is equal to mu2 and is equal to mu3. So using this chemical potential we get two equations for these phases. For each component equilibrium the two equations are necessary. Which are these two equations? So simply the equation first, mu1 is equal to mu2 and mu2 is equal to mu3, and the second equations, mu1 is equal to mu2 and mu1 is equal to mu3. We know that chemical potential for each phase should be equal. Okay, now for using this term we get two equations. You can see here the first chemical potential equal to second chemical potential, the second chemical potential equal to third chemical potential, that is the first equation. Again in second equation the first chemical potential equal to second chemical potential, and again the first chemical potential equal to third chemical potential of third phase. So we got two equation from this condition. Okay, let me clear again. Okay, just focus here, I am explaining you once again. If we have system, what we are trying to finding, what we are trying to finding out, if we have to degree of freedom, total number of variables, we are here trying to find out the degree of freedom, the unknown variables. Okay, total number of variables we have find already. Okay, minus number of relations between them. Now we are trying to find out the relation between these variables. Okay, so we got total number of variables p c minus 1 plus 2. Okay, now we are trying to find out the number of relation between them. So suppose we have considered a system a plus b plus c which having three phases p1, P2, P3. Okay, so as per chemical equilibrium, according to thermodynamics law, which says that the chemical potential for each phase should be equal. Okay, so from this chemical potential we get two equations. Okay, so we need two equations to solve this equation. So first equation, that is a mu1 is equal to mu2 and mu2 is equal to mu3. We know that the chemical potentials are same for each phase. That is the one equation. We got the second equation, mu1 is equal to mu2 and mu1 is equal to mu3. So we got two equations. So you can just simply think that for three phases we got two equations. What I am saying, you just focus here. For three phases we are getting two equations. For four phases, how many number of equation we get? Okay, simple question here, simple logic here. For three phases, we get mu1, mu2, mu3, that is a chemical potential. From that, we got two equations. So basically, these two equations for the three phases. So for four phases, if we have four phases, P1, P2, P3, and P4, how many number of equation we get? Mu1, mu2 equal to mu3, mu3 equal to mu4. Simply, we get three equations. We get P1, P2, P4 are number of phases. Okay. For suppose for phase 5, how many number of equation we get? We get four equations. For phase 6, we get five equation. For phases 7, we get equation 6. So simply we are getting less than one phase number of equation in simple words. So we can write here p minus 1 means जेवढे फेज असणार त्याच्यातून -1 करायच्या आपल्याला काय भेटून जाणार नंबर ऑफ इक्वेशन्स. सो इफ वी हॅव 6 phases then -1 equal to 5, then we get number of 5 equations for number of p phases. Okay, so this is the concept for here. I'm trying to find out the number of relation between them. You just focus here. The entire concept is hide in this equation. This is extremely simple topic. Extremely simple topic. Okay. Hope you get the concept here. The concept is only if we have three phases, we got two equation. If we have four phases, we got four equation. If we have five phases, we will get four equation. If we have six phases, we will get five equations. Okay, now let me talk about the in terms of concentration. If we have number of components, consider the system here. Okay, just consider the system here. Just consider if we have a system where C1, C2, C3 to Cn number of components. Okay, so this will be equilibrium with C1, C2, C3, Cn, C1, C2, C3, C1, C2, C3. So suppose this is a phase 1, this is a phase 2, this is a phase 3, and if you go here, this is a phase n, means number of phases for number of component of system. Okay. So what actually I am saying you, if we have n phases means number of phases, then what will be the number of component? That is a Cn. Okay, if we have number of phases, then we have number of components. For number of components, we have number of phases. So we can write here for number of components, for number of component, for number of phases, we have p minus 1. What are the equations for three phases? We have two equations for three phases. We have three equations for four phases. We have four equations for five phases. For number of phases, we have p minus 1. And for number of components, we have c. So c into bracket p minus 1, it is the actually relations between the number of variables. Okay, what is c? P minus 1, it is a relation between the, or you can say that the total number of non variables. as per your textbook, but actually it is the relation between the variables. What is the relation? And you can say the number of equations required for equilibrium, for sorry, for each phase. So what is the Cp minus 1? The number of equations required for each phase for any component, for any system, for given compound. Okay. Or you can say that Cp minus 1, that is the number of relation between the variables. So we get here total number of variables, and we also get here C p minus 1, number of relation between them. Then we can write here p c minus 1 plus 2 minus c p minus 1. Okay, now f is equal to, that is the f is equal to, we know that the degree of freedom, that is the unknown variable that required to fix. So pc minus p plus 2 minus cp plus c. Cp get cancelled, and the remaining term will be C minus P plus 2. So that is the phase rule. So that is the phase rule. So two important conditions are required. Two important things are required to derive the phase rule. You must remember the conditions for equilibrium. What are the conditions? The condition first was thermal equilibrium. The second condition was, what is the thermal equilibrium condition? The temperature should be equal for each phase, for any system which is in equilibrium, for any system who is in equilibrium, which having same temperature for each phase. That is the first condition. The second condition was mechanical equilibrium. The pressure should be equal for each phase. And the third one, an important one condition, that is a chemical equilibrium. The chemical potential should be equal for each phase. These are the most important conditions for any system which present in equilibrium, any multi component system, okay, which is present in equilibrium. If this condition satisfy, so system will be in equilibrium. If this condition will not satisfy, the equilibrium will be disturbed. Okay. For phase derivation, for phase rule derivation, we mostly need degree of freedom, that is the total number of variables, means and number of relation between them. How can we determine the total number of variables? Simply, we need to determine the composition of each phase. How can we determine the composition of each phase? By using the concentration. Suppose again I am explaining you here, you can just focus here. If we have system, multi component system,